Hello, my name is Gizem Ateş. I'm a PhD candidate in Western Norway University of Applied Sciences. Today I will talk about our study in force and gesture-based motion control of human-robot cooperative lifting using IMU. Co-lifting uses humans and robots' strengths in carrying a common object. For that, we use IMUs, which provide a variable human motion tracking solution which is insensitive to occlusion, obstacle in line of sight, etc. For upper body human motion estimation, we use an orientation-based biomechanical model estimation. It is based on using estimated orientations of individual IMUs and calculating the rotation between consecutive IMUs in quaternion representation, and then extract 3D human joint angles. We have modeled the upper body as 13 degrees of freedom. Since we are mapping human motions to robot motions relatively, the neglected parameters in modeling, such as constrained degrees of freedom, soft tissue artifacts, do not cause any critical problems. There are 4 states defined under 3 roles. Idle and approach states are under human leadership, where the human leads the robot to cooperatively lift the table, whose initial position is unknown for the robot. In the idle state, there is no data transaction, where human can jump at any state. In the approach state, the data transaction is only one directional, which is the motion of the merged hand pose that is calculated as chest to wrist transformation of each arm and then merged with adjustable scales. The co-lift state is belong in shared leadership role, where both human and robot interactively change the leadership role. A directional compliant force is set by the robot, and the direction can be changed by the human elbow motions in the state. The release state is belong in robot leading role, where the robot takes upon the leader role and the human follows robot. A short demonstration of a full cycle is shown. The release point is known by the robot, and the experiment is designed to exploit the humans and robot strengths in robot accuracy in releasing the object and human cognitive skills in deciding the initial pick point of it. This study is an enhanced version of our previous study where only human motions are used, no force enhancement. There were only 2 dynamic roles, human leading and robot leading. The plot on the left shows human hands motions and the robot end effector motions in different states. The improved smoothness is easily detectable. Also, we attached a spare IMU on the table to measure the orientation and acceleration of the table to relate the error and jerk. The effort in the previous study is visible with a relatively aggressive fluctuations in the table orientation. Similarly, the bigger magnitude of acceleration in shorter duration shows that the jerk of the table was higher in the previous study, whereas we enhanced these shortcomings in the study. This is the end of my speech. Thank you for your attention. Please contact me if you have any questions.